Okay, welcome. This is Ken Peters again, and this is the final lecture, the sixth lecture in our series of short lectures on a review of petroleum geochemistry for basin modelers. And again, we're presenting this to our Stanford BPSM students, but we're also making this available to our industrial affiliates in the Basin and Petroleum System Modeling program. So the final lecture today is going to be on gas geochemistry. There's a lot to learn in gas geochemistry. This may be the longest lecture of all six lectures that I will give. I do want to talk about especially biogenic gas generation. I think there's a lot more work that can be done there to improve our abilities to predict methanogenic or biotic methane. So let's proceed. I want to talk about at least these topics. And again, this is boiled down from a course that I normally take 10 weeks to teach. This one section involves a week or two of discussion. So I want to talk about methane and light hydrocarbon gases. I certainly want to talk about methane hydrates a bit. The origin of carbon dioxide, which can sometimes be a major issue in drilling wells and in production, nitrogen content, and of course hydrogen sulfide. And you can see some depictions of those compounds down here below. That's methane on the lower right, and that'd be CO2, and then the other one there is hydrogen sulfide. Okay, well, hydrocarbon gases, as we discussed a little bit earlier in one of the earlier lectures, is something that they can be characterized by isotope composition. And of course, the PD belemnite standard is defined as 0. That's sort of marine carbonate. And our organic materials, marine plants, plankton, land plants, have negative carbon isotope values relative to that PD belemnite standard. And if you look down here at wood and peat and coal, as well as oil and gases, they're all quite negative. And especially the microbial gases, the kinetic isotope fractionation can be significant because those microbes, when they fix carbon and they create methane, they're selective and prefer the light isotope of carbon. C12 as opposed to C13. And so you get some very negative isotope values for microbial gas. Let's talk a little bit about gas seeps. There's been a lot of gas seep analysis in the past, and there still is a lot of work looking for gas seeps, either visible or invisible. And seeps, when they're actually visible, they can assist in exploration and prove the existence of a petroleum system. The underwater seeps can be detected by gas chromatography. We can see them as bubble trains using side scan sonar and so forth. However, seep gases can be of several origins. We can get thermogenic gases. If you're searching for thermogenic hydrocarbons, that's a good thing. They can also be biogenic. And in some cases, that's just a superficial product of microbial metabolism in the shallow sediments. Now, more recently, people are very interested in biogenic gas accumulations. It's a special issue to preserve those biogenic gas accumulations because, of course, they're formed very recently by these microbes, these methanogens, at very low temperatures actually compared to thermogenic origin. So you need to have some special means to trap those biogenic hydrocarbons. We'll talk a little bit more about that later. I want to clear up sort of an issue with the term biogenic. There are actually sort of two ways that this term is used by geochemists. First, biogenic versus abiogenic. Yeah, there are abiogenic hydrocarbons. They're formed really with no microbial, no organism involved. They're abiogenic hydrocarbons. There is primordial methane, for example, which is abiogenic. You can find primordial methane in some chondrites from outer space, basically. But also, we a lot of times use the term biogenic as a counter to thermogenic. That is, biogenic gas that's actually manufactured by organisms versus that which is cracked by high temperature thermal processes in the subsurface. For item 1, biogenic means that once living organic matter is the source of the petroleum, not inorganic carbon from the deep earth. And for item 2, biogenic means that the gas originated from microbes and not by thermal cracking from the kerogen or from oil. So here is here are a couple of gas chromatograms. This is actually not a true statement up here at the top where I say pure, biogenic gas is pure methane. There is evidence, pretty convincing evidence that very small amounts of ethane and propane, actually even propane, can be generated microbially, but this is pretty much a true statement. By far, the microbial gases are dominated by methane. We call that dry gas. Thermogenic gases, on the other hand, you see we have a lot of C2 to C6 hydrocarbons that are also generated by this cracking, this thermal cracking process, which is much less selective for bond cleavage than microbial gas generation. I think microbes can be highly selective when they break out methane, and you get a very strong isotope fractionation in carbon for that reason. Here, the isotope fractionations are not as clear-cut, although these are still quite negative compared to the crude oil, for example, or the source rock that the organic matter is derived from. So here's a little complex figure, but it basically shows you a little table with some simple sort of cutoffs for differences between biogenic and thermogenic gas, and also wet thermogenic gas. Primary biogenic gas is dry. It's 98% or more methane compared to C1 to C5. And isotopically, we say that's light. The isotope compositions are quite negative, right? Maybe even more negative than -85. On the other hand, a dry thermogenic gas, that's a really high maturity gas. It's also dry, but the isotope composition of the methane is generally much heavier, much more enriched in carbon-13. And of course, the wet gases, wet thermogenic gases, they're wet because we have a lot of C2 plus hydrocarbons, and they show sort of intermediate, the methane shows sort of intermediate isotope composition. Now on the photomicrograph here on the left, this is an electron SEM scan that shows you some methanogens. These are really unusual organisms. Methanogens are obligate anaerobes. That means they only function under anaerobic conditions. Oxygen is toxic to them. They produce pure methane, essentially pure methane, by using a carbon substrate and energy. And there are two types. Hydrogenotrophic or hydrotrophic methanogens use CO2 as the carbon source and hydrogen as an energy source. So they reduce the organic matter, and the CO2 and H2 react to produce methane. Acetotrophic methanogens, they use acetate as a substrate. So here's the acetate anion, and they basically ferment this to produce carbon, methane as methane and CO2. These two processes are conducted by different types of methanogens, different communities of consortia of methanogens, and sometimes other organisms, but generally the methanogens are the ones that make the methane. Okay. Again, this is kind of a summary of the table I showed you a little bit earlier. Biogenic dry gas occurs at shallow depths. It's tough to, you need a special mechanism to trap that biogenic methane. Thermogenic dry gas also occurs, but it's isotopically heavy in carbon. And then we have the oil window here, catagenesis, the oil window. We generate gases associated with that too, and they show intermediate isotope compositions. Okay, now these are some figures from Milkov and Etiop in 2018, and these update some of the early work done by Martin Scholl. So Alexei Milkov has published this very recently based on a larger sample set than was available to Martin Scholl. But these are sort of fields that can be used to help describe what kind of gas you may be dealing with. Here's the carbon isotope value, the hydrogen isotope value, sorry, of the methane. Sometimes that is referred to as delta D, as in deuterium. Deuterium is got 2. It's a mass of 2. And here's the carbon isotope value of the methane, and you can see we can distinguish these different zones. These are sort of revised genetic fields. Here, CR is the CO2 reduction that I just talked about. We also have the methyl type fermentation, the acetotrophic type of fermentation. That's also in this area down here. This would be secondary microbial gas. There's primary microbial gas from methanogens, but there's also secondary microbial gas. It's a major source of gas, as a matter of fact, in some fields where the oil has been converted directly to methane by methanogens in the rock. EMT here is the early mature thermogenic gas. OA is oil-associated gas. And of course, LMT would be late mature thermogenic gas. On the right, we show some of these processes and the direction that the isotope compositions take as a result of these different processes. Biodegradation, thermal maturation. TSR refers to thermochemical sulfate reduction, which we will talk about a little bit later. It's a major process for degrading heavier hydrocarbons. Alexei Milkov has several of these figures. Here's another one that shows the carbon isotope value of the methane against the wetness. This is one way of measuring wetness, C1 over C2 to C3. And again, there's overlap. There's a lot of overlap between these different classifications, but this helps at least in helping you to decide what the origin is of these gases. Okay, so, and here's a third figure. This is now the carbon isotope value of the carbon dioxide and the carbon isotope value of the methane. And so here, for example, is a way of distinguishing primary microbial generation, primary microbial gas from secondary microbial gas. They're isotopically distinct in the CO2, and secondary microbial gas shows an inverse correlation between CO2 and carbon and the methane isotope values. So again, here are the processes. I'll leave you to look at the Milkov and Etiop paper if you want to look more at in more detail. So here's an early quiz that I will go through with you to speed things up here a little bit. This is some data from Lawfrey and Baldassar in 1998, and I just pulled that data from their paper, and I'm showing you pretty complete isotope and compositional analysis of some gases. And you can look at these gases, and based on what I just told you, probably say something about the origin of these gases. First thing to look at, of course, is the C2 plus content. You remember we said that methanogenesis, methane genesis, biogenic methane is really almost pure methane. So this is not a biogenic gas, nor is that one, nor is that one. They all have C2 plus. So you can say these are thermogenic gases. You can also have a look at these gases here. For example, this one has isotopically a little bit enriched in carbon-13 compared to that one, and this one is more enriched still in the methane, and it has less, this one has less C2 plus, and that one has even less. So you can say, for example, between 1 and 2, they're both thermogenic, but it looks like this one, number 2, is thermally more mature. And you know, you've also got isotope compositions on the hydrogen, which you can plot on those plots I showed you just a minute ago, and isotope composition on the C2 and the C3, the ethane and the propane. So this one, number 2, is more mature than number 1. Number 3, I included in this figure because it's really rather anomalous. One could almost come to the conclusion that this is an abiogenic gas. We'll explain this a little bit later, but you'll notice the isotope composition of the methane, the ethane, and the propane for these 2 thermogenic gases follows a normal sort of Rayleigh distillation pattern where the ethane, the propane is isotopically heavier than the ethane, and the lightest is the methane. And you see that in this gas as well. So that's a normal isotope range that you expect for each of those compounds. You see a reversed isotope distribution here where actually the methane is isotopically the heaviest. Yeah. And then the ethane, and then the propane is the lightest. This could indeed be an abiogenic gas, or many times, well, these are pretty rare, but when you do see these, sometimes you can explain them as a result, not of being abiogenic, but actually as a result of mixing of gases of different origin. Here, number 16, here is another, looks like thermogenic gas. This one is isotopically quite light compared to, say, 1 and 2 up here. So I would say 16 is probably much less mature. It's a much less mature gas than 1 and 2. Yeah, and these gases down here are cold bed desorption gases. You notice there's very little C2+, and there's a range of isotope composition. So 22 and 23 here are sort of mixed microbial and thermogenic gases, probably fairly low maturity. This one, number 24, looks like it's a more mature thermogenic product, probably, you know, we would plot probably in the oil-associated zone on some of those figures, but it's coal bed gas. So it's, you know, coal bed gas has a lot of sort of methanogenic methane to start with, and then the thermogenic gas mixes with that. So this is a little more mature gas. So let's look at a graph. This is a graph that's been used for many, many years to compare compositions of some of those gases. And this is from Alan James from Shell back in 1983. And it actually works quite well for getting you an approximate level of thermal maturity. This is sort of a very seldom used scale anymore. It's peculiar to 1 or 2 oil companies, and most people don't use LOM, level organic maturity, anymore. But I've got the reflectance scale on here, equivalent reflectance scale on here. And what you do to fit yourself onto this graph is you take the difference in the carbon isotope value between the carbon numbers. So here's the difference between C1 and C2. And then you take the difference between C2 and C3. And I just went to that table and used those and slide the data to the right until it fits. So the C6, the sample number 16 is clearly less mature than sample number 1. And sample number 2 looks like it's the most mature. These are sort of Rayleigh distillation. These, you can calculate these. These are Rayleigh distillation, basically fractionations in the gas carbon numbers. As you get more and more mature, the gases start to look isotopically very similar, and they converge on each other here. Down below, we have the thermal alteration index as well. So you may see LOM in some very old papers. For example, we talked about Quinn Passey's delta log R method. They refer to LOM, but most people don't use this anymore because this scale is not linear with the reflectance scale. It's, in fact, you can't fit it with a polynomial in any reasonable or easy way. So everything pretty much maturity-wise is described even in terms of gases, vitronite reflectance equivalent. Now this is a common issue in gas geochemistry. We have cases where we have mixtures of biogenic and thermogenic gas. And you know, the thermogenic gas is always C2, has all C2 plus C1. Methanogenic gas, the biogenic gas, is pure C1. So you can use this Moses-Chung plot where N is the carbon number, right? So here's methane, and you can use that to plot this sort of a diagram. So we know the thermogenic gas should probably have, just by sort of Rayleigh distillation, an assumption of Rayleigh distillation type cracking, methane isotope composition down here around minus 38 or so. But in fact, it's down here. So this is good evidence for a mixing of a biogenic component with that thermogenic gas based on the trend from C2 to C5. And you can actually calculate then the proportion of the biogenic methane mixed in that mixed gas. You can also do other things. You can extrapolate this C2 to C5 trend to extrapolate an extended sort of the isotope composition of the kerogen or the oil that it came from. Chung, however, observed that that oil is generally isotopically lighter than the intercept of the on this plot, on this natural gas plot. So, for example, my experience in the San Joaquin Basin is that the C2 to C5 gas extrapolation indicates about minus 21 per mil, while the associated oil is usually around minus 23 or so. So it's a little bit off, but it does a pretty good job of predicting what the isotope composition of the kerogen might be, and that's a useful thing to try to correlate a thermogenic gas with its source kerogen. Kerogen is typically about 1.5 to 2 per mil isotopically lighter in carbon than the oil that it generates. But again, here you have an extrapolation to get the methane, and here's the actual methane measurement. You can actually calculate a biogenic component in that oil. Here's actually, these are 3 gases that I actually looked at. They were proprietary gases when I worked on them, so I've given them labels A, B, C, and these gases I know are genetically the same. They're coming from the same source rock. The thermogenic component, you can see the thermogenic component here matches up with the C1 here. So this A would be basically a pure thermogenic gas. Yeah. In B, you can see we have this discrepancy here between what the C2 to C5 says the isotope composition of the methane should be and the actual methane measurement. So there we've got a biogenic methane component in there as well. This gas, the C, is a beautiful example of mild biodegradation of the gases. And what happens is the methane gets isotopically lighter, and some of these other compounds get isotopically heavier, and so the whole axis of the correlation shifts. Turns out that some of these compounds are a little more susceptible to biodegradation than others, and I'll come back to that in a minute. B and C, if we want to estimate their relative thermal maturities, we can use, well, probably the most recent paper would be by Berner and Eric Faber. There's a relationship between the ethane and propane you can use to predict the approximate vitrinite reflectance equivalent of those samples, right? And in terms of the biodegradation, yeah, some compounds are more susceptible in the gas range than others. This is from a paper by Barry Katz, and I think it's a beautiful example of, see very negative isotope composition for the methane. Yeah, but if you go to the C3, NC3, and the NC4 and the NC5 isotopically, this gas, those are isotopically enriched in carbon-13. And that's because those compounds have been preferentially biodegraded, and what's left is enriched in the carbon, is enriched in carbon-13. So you can actually see the sawtooth pattern in this gas that's been mildly biodegraded. The branched hydrocarbons, as we know from the earlier discussion on oil correlation, branched hydrocarbons are a little more resistant to biodegradation than the normal alkanes, where the microbes basically just chomp down the chain from either end. As soon as they hit a branch point, it's difficult, a little more difficult to conduct simple biodegradation. Well, I want to spend some time talking about biogenic gas generation. This is a topic that I think is of interest to many people, and this is an entry in commonly used software. This is Petra Mod, and Petra Mod allows you to calculate biogenic gas generation, and there are three approaches here that can be used. The user selects a component, biomethane, it's called biomethane, and then chooses among these three methods, okay? So we're going to discuss each of these a little bit, the Gaussian distribution and the Middelburg especially I want to talk about. All of these in this approach are basically a thermal control on biogenesis. Now we know that these microbes are like us. They're very sensitive to the environment around them. So it's not just temperature sensitivity that controls methanogenesis, and that's the real limitation in many software, basin modeling software that are out there, is they try to model methanogenesis based on the temperature sensitivity of these methanogens, but of course they're also subject to other things like they need a certain substrate. If that substrate's not there, they're not happy. Or if there's another type of consortium present, like sulfate reducers are producing H2S and there's sulfate present, the methanogens can't compete with those sulfate reducers. So there are other things involved in methanogenesis than just temperature, but this is the attempt that many people have made at calculating methane generation. So let's talk about the Gaussian. This is within Petra Mod now. This is the biogeneration format here, and the operator, the investigator here, has clicked on Gaussian distribution, and the default here, the mean temperature is 50 degrees C, and the standard deviation is 10 degrees C. Okay, so this is Gaussian. So you can see what the program is going to do. It's going to look at the basin history, or the history, especially of the more recent sediments, and it's going to say, well, the microbes really aren't very happy here, 20 degrees centigrade, and they're not very happy over here, but around 50 degrees centigrade, we're going to have this Gaussian reactivity increase. Well, it looks to me at least like this default peak is far too high, and I'll try to support that with some evidence in a little bit here. So Gaussian is one approach. Kinetics for options 1 or 2 and not based really on published papers. I've looked and looked and I can't find them. For example, there are 2 options for entering user-defined first-order rate constants. Here's a little entry that you can make to do that. Rate constant is independent of temperature or Gaussian temperature, right? Or the rate constant depends on temperature or Gaussian temperature. This is generally not recommended. I won't talk much more about this one. Some interpreters use default for degradation rate from a paper by Johnston et al., which is about 13 milligrams of carbon per kilogram per day. Those are from laboratory experiments, and unfortunately, this may not be the best degradation rate to assume here, because these are based on air sparging experiments. Well, air sparging is they're adding oxygen to these laboratory cultures, and that means that the organisms that are doing the reactivity, the degradation of the organic matter are aerobes. They're not anaerobes like the methanogens. So if no rate constants entered, the generated amounts are equally distributed over time. This may be a little bit dangerous assumption here. Anyway, here are some data from the literature. This is from a paper by Rutkowski, and one of my students actually brought this to my attention, and she thought that, well, this must be the justification for this, this approach that's used. However, I had a look at this paper, and basically all of these organisms I know about, Actinobacter and Pseudomonas and Flavobacterium, these are all aerobes or facultative anaerobes, and they're bacteria. They're not methanogens. They're not anaerobic methanogens. So yeah, maybe these organisms function in the same way, the anaerobic bacteria maybe, in the same way that methanogens do, but the temperature maxima may not be the same. So T-opt here is the optimum or the maximum growth that was observed in laboratory culture for these 16 bacterial strains. And it turns out to be 32 degrees C. T-min and T-max are where the organisms aren't happy at all, right? So T-opt on this case is defined by these authors, Rotowski et al., as the place where the microbes do the most conversion, the maximum growth rate. Well, if you look at some other papers, you know that based on also lab work, acetoclastic dominates hydrogenotrophic methanogenesis at low incubation temperatures. So remember I said there were two types of methanogenesis. There's still a lot of controversy about which of these is involved in shallow sediments, which is involved in oil reservoirs at depth. Some of the work seems to suggest that acetoclastic is dominant in shallow sediments, the kinds of sediments we're talking about. And I'll show some evidence for that. And some other evidence suggests that hydrogenotrophic methanogenesis may be more important in oil reservoirs where we get secondary methane generation. There's this paper by Fu et al. In 2015, and again, they're working with cultures. Looks like the low incubation temperatures are what really prevail for these acetotrophic methanogens, 15 degrees centigrade, as opposed to 25 to 35 degrees centigrade. So these temperatures are significantly below the 50 degrees C default in Petra Mod. Now, of course, in Petra Mod, you can change that default and slide that Gaussian distribution to the left to lower temperatures if you want. So let's talk a little bit about now this third option, which is the Middelburg approach. It's MIDDEL, Middelburg, in Geochemica, Cosmochemica Acta. Actually, this is the correct reference, not this one. Middelburg actually looked at the degradation of organic matter with depth in basins. And he came up with some parameters. One is the apparent initial age, which is not the age of the organic carbon. That Middelburg defines as T. And also he has a different way of getting at this other variable here, the age of the sediment itself. He calls that T. And here it's defined as the burial, the sedimentation rate, the burial depth divided by the sedimentation rate. Well, even in shallow sediments, the burial rate can vary. So this is, vary through time. So this is a little bit risky here. So anyway, let's talk about the Middelburg approach. This is his paper right here on the upper right. And one of the principal results. What he did is he looked at organic carbon versus time, and he plots the log of one against the other, and he gets a straight line. And that's rather, to me, that's rather amazing. It didn't matter where the samples were from or what kind of organic matter it was. He got this, basically the same slope. So this says the organic matter is being degraded at the same sort of rate with time. And Middelburg came up with this equation. The rate is an exponential of the time exposure. Well, he did modify that, and I'll talk about that in a minute. This is the simplest expression of what he found, and what there was a paper by Pinheiro et al. That used Petra Mod to calculate then the TOC degradation rate. So they plugged TOC into this equation. TOC degradation rate now, they used the Middelburg kinetics, right? Well, there are two assumptions here that are actually incorrect in this paper. For example, actually, when you look at Middelburg in detail, K is equal to 0.16 times A plus T. So he's got the age of the sediment, but he also has an additional factor here that he calls the apparent initial age. Okay, so it's not just the age of the sediment, but also there's a very important factor here called the apparent initial age. The Pinheiro paper did not include that A factor. So let's look at that. In actually the Middelburg paper, if you look, they have a table that is basically comprised by these first three columns. Sediment site, the A value, which is calculated. He shows you how to do that in the paper, Middelburg, Jack Middelburg. And here's some references. Well, I know these references, and I've looked at this. Look at the difference in the A value. So that's a big difference that's going to plug into this equation. And if you ignore it, you could be in real trouble. And I added this fourth column here. From these papers, I know all of these depositional environments can be described in gross terms as being anoxic or oxic. If you go to Saanich Inlet, you know, we know that Saanich Inlet, present day, or Cape Lookout Bight, these are strongly anoxic sediments. You know, the water column is oxic, but the sediments themselves, very low EH, the concentration of oxygen in the sediments is below 0.5 milligrams per liter, right? So it's very, very low, basically oxygen absent. Whereas you go to the Central Pacific or the hatteras abyssal plain, I remember we talked a little bit about this when we talked about the center of the Pacific being basically a desert, or the organic matter, the amount of organic matter that gets to the bottom sediments. That's because the water columns are so oxic that very little organic matter gets down there. And you see the effect on this apparent initial age. Wow, this apparent initial age really is going to change this equation, right, quite a bit. So this A value is absolutely critical that you include an estimate of the initial apparent age, and that's related to the EH, the redox potential in the depositional environment. Another assumption that was made in the Pinheiro paper is that the TOC, all of the TOC is available to be converted to methane. And that's clearly not true. We know that. There are multiple papers out there that show that. Not all TOC is converted to methane. In fact, only a small fraction of it is available or reactive to make methane. So here's a slide that I showed you actually quite early in the course. We talked about oxic depositional settings, and you see very little of the organic matter is going to be preserved under these conditions because aerobes are very efficient at destroying organic matter. They will eat that little diatom and it'll go through the guts of different organisms. And when it gets to the sediments after days or months, it still has many, many years exposed to oxygen in the interstices between the silt or sand or mud grains, the clay grains here in the sediment. So much of the organic matter is destroyed here. So that initial, you know, that apparent initial age is going to be a big number. Once you get down to the sulfate reducing zone, the destruction of the organic matter occurs at a much slower rate. And of course, in the methanogenic zone, you're going to make methane by CO2 reduction or acetate fermentation, as I described earlier. But you know, there's not much left here to do that under these cases. So in an anoxic setting, like in Saanich Inlet, you've got anoxic bottom waters. You have laminated sediments because the oxygen is all used up. There are no aerobes to bioturbate the sediment, and you're going to get a much lower value for that initial apparent initial age. Right? So yeah, that's something to keep in mind when you use the Middelburg kinetics. And again, the upper and lower limits for the methanogenic zone, it's going to be really tough to model that using software that just considers temperature as the main control. Certainly, certainly these methanogens are temperature sensitive. At least the ones that do methane production, they're quite sensitive. These are, of course, archaea. There are some thermophiles that handle very high temperatures, but these methanogens are not among those in the archaea. These guys are very sensitive to temperature, and 80 degrees or so is really too hot for them. They don't like that. So, we've got the acetate fermentation and we've got the CO2 reduction, two different approaches for making methane. Here the substrate is acetate, and here the substrate is CO2 and hydrogen. Okay, but it's not just temperature, but it's also the availability of these substrates. This substrate, for example, is food up here in the sulfate reducing zone. So a lot of times these methanogens are going to be starved for their substrate. If they're acetate fermenters, they're going to be starved for that substrate because it's already been largely consumed by the sulfate reducers higher in the sediments. Also, some of the reactions here that that the methanogens go with, like making methane, are going to be taken apart here by, here's reverse methanogenesis right here. These sulfate reducers are using sulfate from the water column or the sediments to oxidize the organic matter. So that's going to limit the upper zone here of the methanogens. They can't compete with these sulfate reducers. And also the lower limit is a fuzzy boundary as well. It's not just temperature. There is temperature sensitivity here, but the lower limit is also going to be, availability of that, of those substrates to allow those reactions to proceed. So it's a little more complicated than simple thermal modeling. So here is kind of what I've just told you in a graphical form. We have in sediments, we've got these complex biopolymers, things like cellulose and lignin and proteins, and these can be degraded by different consortia of aerobes and also of sulfate reducers and other organisms, as indicated in this previous figure here, right? Sulfate reducers, yeah. And we end up with monomers that, of course, are readily degraded: fatty acids, sugars, amino acids. These are food for these different consortia, and some of those products and these monomers are basically, again, the substrates for these methanogens. So if those are preserved down into the methanogenic zone, then the methanogens are happy. If they undergo CO2 reduction, yeah, they're going to take CO2 and hydrogen, and they're going to make methane. Yeah, if they're the type that does acetate fermentation, they're going to need that acetate to make that reaction go. Yeah, so these are two different reactions, as I said, types of reactions. As I said, the archaea, the methanogens that do this are different consortia that may compete with each other, and there's some controversy about which of these is more important in shallow sediments. I'll provide some evidence that suggests it's really acetate fermentation that's the more prominent reaction in shallow sediments. One thing to notice here is that if you look at the mass balance here, the carbon to oxygen ratio that's lost, you see it in the atomic ratio of carbon to oxygen is about 1 to 2, whereas in acetate fermentation, it's 1 to 1. So Chris Clayton actually looked at this and had some nice insights. Here he looked at his, we've got our Van Crevelen diagram here. And he said, well, okay, I've got some sediments in West Africa and the Peru margin. I've got some peat here. What happens if I, during diagenesis, convert these by moving along this line to just the beginning of thermal maturation or catagenesis here? So all of this maturation from here to here and from there to there is diagenetic loss of hydrogen and of oxygen. Well, I just told you what those ratios were between the different methods here, CO2 reduction and acetate fermentation. If you look at that and do a calculation of the amount of carbon that's going to be lost as a result of these products, you're going to see for type 2 or type 3 organic matter higher values for the amount of carbon lost by acetate fermentation than by CO2 reduction. Okay? So that's an interesting observation. Here's the acetotrophic or acetate fermentation. So there's some key questions that we can start to address here. What volumes of methane can methanogens produce? We can get at that from this Van Krevelen diagram. And how fast can they produce that methane? That involves some kinetics. And we're going to have to make some assumptions there that we'll talk about in a minute. We're dealing with obligate anaerobes. They can't compete with sulfate reduction reducers. They have a limited temperature range. That's that Gaussian approach. But they also have an issue with substrate supply. So they can be starved if those substrates have already been used up by consortia of different organisms in shallower sediments. So let's just remember these sorts of numbers. These are the amount of carbon lost in this methane production here. And that's kind of interesting, isn't it? It's not 100%. Remember that Pinero et al. Paper, it's a fraction of the organic carbon that's available to make methane. So there's another way to get at this that's totally independent. And if you look at the paper by Rasewell and Robert Berner, this shows carbon to sulfur ratios as a function of thermal maturity. Again, this is vitrinite reflectance under immersion oil. And they have collected a lot of data from around the world from different sediments. And they said, well, how much carbon is lost going from diagenesis to the beginning of early catagenesis here? And this sample right here is key. These are quaternary sediments. And for basically the average for most quaternary sediments, the carbon to sulfur ratio is about 2.8. Now, I'm not going to go into the details here, but basically this carbon to sulfur ratio is stable below the sulfate reducing zone. Yeah, here, it's stable below the sulfate reducing zone. So any subsequent decrease in the carbon to sulfur ratio is due to carbon loss. If you make that assumption, and that seems to be a pretty good assumption, you can actually make a calculation here, Rasewell and Berner's data, 2.8 to say 2.03. Yeah, that's going to give you about 27% carbon loss during diagenesis. Now, this is a little bit deceptive because this 2.03 right here, is a sample that involved a reflectance of about 0.65. So, catagenesis is 0.5. So this is probably a little bit of a high number. This one right here is probably a little bit high. And this one certainly is high because it's 0.7% reflectance. Okay, so if you calculate the carbon lost here, it's going to be even more. But from here to here, the carbon loss is about 27%, which doesn't differ too much from what our calculation from the Van Krevelen diagram was, which is around 20 to 22% carbon loss. So it looks like acetoclastic methanogenesis is probably the major mechanism here. Now there's another paper that I was looking at by Morris and Berner that goes through a lot of math. I'm not going to include the math here, but they come to the conclusion that under certain conditions, sort of ideal conditions, you get about 17 to 27% of the total organic carbon as being labile, right? Labile that will affect, that can be used then to generate, methane. This is the labile TOC. So there's some complex math involved here, some loss due to oxidation of the sulfide and oxidation of the TOC, but buried sulfide, the C-to-S ratio is down here. So that's what their conclusion is. Again, that's sort of in that range of acetate fermentation. And if you look at some papers that show carbon burial efficiency versus sedimentation rate, this is a paper by Dale et al. In 2015. This is kind of interesting. This says, gee, about 70 or 80% of the organic carbon is going to be buried, right? Under these sort of oxygen deficient conditions, or euxinic conditions, another term for anoxia up here. 70, 80% is going to be preserved. Well, that means that available is the difference. So that's around 20 to 30 or so percent organic carbon. So we've got several, 4 different independent lines of evidence that suggest that maybe acetoclastic methanogenesis is the major process in shallow sediments. Now, there's a paper by Zekas and Winfrey, and Chris Clayton uses this to get his optimal temperature for conversion or methanogenesis. This is nanomoles of methane in the sediment. And these are for incubated organic rich sediments from this paper. And you can see here that depends on the depth, the efficiency, the amount of methane that's generated. These sediments right here still are having an effect from sort of oxygen in the sediment. So what Clayton uses is he uses these data from the 10 and 18 meter model to calculate the conversion rate and also the optimal temperature. And his optimal temperatures are sort of in the range of 35 to 42. Again, that's higher than some other estimates that you'll see, but it's certainly lower than the 50 degrees C default in Petra Mod. Most isolated methanogens have temperature optima around 25 degrees C and upper temperature limits at 30 to 40 degrees C. Here's another paper that makes that statement. So I would conclude that the Petra Mod default peak is a little too high. And of course, you can easily modify that and bring that down, but the default is probably too high. So it looks to me like acetoclastic methanogens are really dominating at low temperatures. And, we have temperatures sort of at 15 degrees to maybe a little higher, maybe 35 degrees that where this all occurs. And we have that microbial community that does that. Well, there is another issue here you got to think about when we talk about optimal temperature for laboratory experiments. That may be misleading, because if you do a lab experiment, you're gonna provide those methanogens with all the substrate they want. So methanogens can be starved. For acetate, for example, these acetotrophic methanogens can be starved for acetate because it might be already used up or largely used up by the organisms in shallower sediment. So, there's another issue here. These low temperature thermogenic, the low temperature acetoclastic species may actually have an early selective advantage over those that work at a little bit higher temperatures. So default peak generation at 50 degrees C is likely far too high. Most methanogenesis probably occurs near 15 to 25 degrees C, and even other methanogens that work, at higher temperatures probably going to be squeezed out and won't be able to compete with those that work at these lower temperatures because they get to the organic matter first. Okay, so here's some data from a paper by Wellsbury, and he looked at the depth profile for the substrate for these acetotrophic methanogens. This is acetate. And one thing he noticed here, this is the gas hydrate stability field. One thing he noticed here is that when you look at the amount of acetate that's available for these guys, it's basically absent in the zone where there could be methanogenesis. So they're starved for acetate. Acetate, though, concentration starts to go up a little bit deeper in the section, and that's where you start to see the methane from acetate forming. That's where you start to see this is methane from, this is CO2 reduction here, and you see the methane from the acetate here. So they basically come up with the concept that you need to thermally activate the protokerogen, the thermally immature kerogen in these sediments. At very low temperatures, you need to be generating additional acetate to feed these methanogens. So they did some experiments. Here's some pore water acetate from heated intertidal sediment, and they're measuring the acetate concentration. Here is the, here's the data, and they kind of fit that to this curve, and they're saying, gee, the optimal temperature for generating acetate from protokerogen by this thermal activation, proposed thermal activation process is around, it's around 30 something to 40 something degrees C. So this may really be the more realistic control on these methanogens in shallow sediments. Here again from Wellsbury, these are the, this was actually data from heated intertidal sediments. And here's actually the data again from samples from the Blake Ridge. You can see in the lab heating, they get this curve. Again, this is the optimum range from methanogenesis from Clayton's work. And here are samples from actual wells where they used the geothermal gradient to calculate a temperature. And there's pretty good agreement between these. They're measuring the acetate using basically these are different types of electrophoresis, isotachophoresis, and enzymatic high pressure liquid chromatography to measure those compounds, measure the acetate here. So it looks like low temperatures are indeed releasing acetate from the protokerogen, and this may indeed be the main control. Now, Chris Clayton took this and ran with it, and I think he's done some really interesting work here. He uses, unfortunately, he uses CO2 as a proxy for acetate. It'd be nice to be able to use acetate, actually measured acetate, to calculate some kinetics, but the data are just not available. So he's going to use CO2, the kinetics of CO2 generation, as a proxy for acetate, right? And the underlying assumption here is that if you've got kerogen with carboxyl groups attached to it, or an ester group here, you can break those bonds and form CO2. All right, here you're going to make acetate, but here you're going to make CO2 from this cleavage here, or from that cleavage there. And he's making a leap of faith here that the kinetics of these sorts of cleavage reactions are going to be similar to the kinetics of breaking an ester group from the kerogen. This may or may not be true, but that's the way it is. He's assuming similar kinetics. And there's an early paper by Dinyao et al. That has some kinetics for the Boone clay kerogen, for CO2, labile CO2 production from that kerogen. And then this was improved upon by some later work by Francois Laurent from IFP. And they proposed sort of three similar reactions with A factors, pre-exponential, and activation energies to account for CO2 generation. Okay, so you can use these kinetics then. Clayton wants to use these kinetics for generation of the acetate, the acetate substrate for the methanogens. So this is kind of an outline of what he has done. A portion of the TOC, only a portion of that TOC is labile. We talked about some of the evidence for that. Also carbon to sulfur ratios. And then you have probable acetate acetogenesis going on here. And then the extent of acetate conversion, he's using the Laurent kinetics for acetate, assuming that CO2 can be substituted for acetate here. And then the rate of methane generation, he's using those optimal temperatures from the experiments that he measured in those sediments, 10 and 18 meters. And by combining those, he can get a methane generated versus temperature. And of course, there are some additional steps here. Many software already approach these steps, surface losses due to diffusion, absorption onto the kerogen, solution effects. You can make calculations. Here's from some data by Clayton, calculations versus depth. So he's coming to the conclusion that typically about 10 to 15% of the kerogen is converted to methane, not 100%, just some fraction of it is, we would call that labile, to be converted into methane. So Clayton has some nice software. It's called Biogenics, and this is in Excel format, and it allows the interpreter to input various data about the lithologies and the temperature and the kinetics. And this has been used in a number of recent publications. This is a publication by Hanneke Verwijs from TSO in the Netherlands. And this shows an example of the Biogenics application to offshore Netherlands. You can see here, this is their burial history. It's a 1D extraction from their 3D Petra Mod model that makes these sort of inputs, sediment water interface temperature, thermal gradient, lithology, sedimentation rate. You have temperature that's predicted through time based on that model. And then you can extract that and use that as input for the Biogenics model. And this then allows you to make calculations about the absorbed, dissolved, free, soluble, and expelled biogenic methane in that setting. It's quite exciting approach. But again, there are assumptions involved. I do want to talk about secondary microbial methane. And that is actually quite distinct from primary microbial methane. You can get methane directly from crude oil in reservoirs. It's anaerobic, again, and it's associated with biodegraded oil. It occurs at low reservoir temperatures, less than 80 degrees, and you end up with dry methane. So this puzzled geochemists for many years. They were looking at reservoirs, for example, in the North Sea, where you had dry methane, almost pure methane, gas cap on top of black oil in the reservoir. So the methane is unusually heavy, minus 40, minus 55, as is the carbon isotope value of the CO2 associated with it. Of course, these methanogens are oxidizing the oil, and they're making methane, and they're also generating methane and CO2. And there's an inverse correlation between the carbon isotope value of the CO2 and the methane because they're related. So there's a nice paper by Alexei Milkov on this, and he calls this the secondary microbial gas factory. This is in Sedimentation pools, and kind of a general summary on West Siberia. Some of the mass balance that people used early on in predicting the amount of biogenic gas was based on huge reserves of presumably biogenic gas in fields like, in many fields in West Siberia. It turns out that a lot of this is secondary biogenic gas. It's still biogenic, but it's formed from oil. So you've got this factory, this oil is migrating upward and being converted by these methanogens in lower temperature zones in the Sedimentation pools here to generate pure methane. So here's an example of this from the Ruskoy field. You have biodegraded oil, and you can see that from the gas chromatograms. This is a whole oil gas chromatogram. And you basically have a prolonged supply of thermogenic petroleum into these cool overlying biodegradation factories. So you end up with biodegraded oil, dry methane, 99.9% methane, carbon isotopes in the range of -40 to -55. And the reservoir temperature is quite low, right? These microbes are temperature sensitive, of course. Okay, here's some more data. You can see the biodegradation here, the floor of biodegradation, and you see some very sort of diagnostic changes. Here's the temperature, again, low temperature. You can see the cyclics are a little more resistant to biodegradation, so their concentration goes up in any liquid that remains. The alkanes, of course, are readily biodegraded. They tend to drop off pretty quickly. C2 plus, yeah, C2 plus is you're getting more and more methane, pure methane, and the isotope compositions are changing as well. So this is typical of these. This is another field. This is Uruguay. This is actually the second largest gas field in the world. And of course, this contributed to the tremendous volume of, quote, biogenic, unquote, gas worldwide. This, of course, though, is secondary biogenic gas. Biodegradation affected the liquids, at less than 1,800 meters depth, and the present day temperature of 55 degrees C. The gas chromatograms, of course, indicate heavy biodegradation of the condensate in the PK1 reservoir and moderate degradation in PK2. Okay? So you've got biodegradation going on, and you see the same sorts of changes that I showed you a little bit earlier in the data above that biodegradation floor because of the methanogenesis. Well, I've highlighted on this figure, again from Milkov and Leon Zhao, the inverse correlation here between the carbon isotope value of the CO2 and the methane. They're inversely correlated, right? So your CO2 here is a substrate, and you're making methane. So the isotope composition of the methane is becoming heavier from that CO2. So isotope composition of the CO2 is quite heavy in these. So that's an involved figure. I'm not going to go into that in detail, but this is basically a Chung plot that shows how this evolves with increasing maturity or level of biodegradation. I'm going to talk very briefly about hydrate stability zones. Most basin modeling software handles this very well. This is physical chemistry, and some of the first work was done by Keith Menvold here back in 1988. So there's a hydrothermal gradient, there's a phase boundary, and the intersection here of the geothermal gradient and the stability, the stability zone of the methane hydrates is outlined here in purple. And you can predict these quite readily using some math. This is what a hydrate looks like when you basically light a match to it. It's ice where the methane is chelated or clathrate within that ice, that gas hydrate. There are more recent papers that go into even more detail. This is from Ruppel and Kessler, and you can look at those. You have gas hydrates in permafrost, you have gas hydrates in marine settings. This figure on the right shows kind of a blow up of this portion of the middle figure here. The BSR is, of course, the bottom simulating reflector, and that marks the boundary between the free gas and the overlying gas hydrate. The purple zone, of course, corresponds to the gas hydrate with dissolved gas, and the yellow regions may have coexisting dissolved gas and free gas. And this figure at the right, again, is that expansion of that seafloor zone from this. And again, our basin modeling software is able to model this, the gas hydrates quite well. And of course, this is an outstanding seal, and that's one of the mechanisms for trapping biogenic methane that's generated at very low temperatures, way before there are really any competent mineralized seals. Okay, so let's have some conclusions on modeling biogenic gas generation. I think that's an important part of this discussion of gases because biogenic gas is a major target for many companies and actually countries as well. Archaea generate primary microbial methane that's dry and isotopically light. Methanogens can't compete with aerobes and sulfate reducers. The principal modes of methanogenesis are CO2 reduction. This is probably the prominent sort of methanogenesis that's occurring in reservoirs, whereas acetate fermentation looks like, at least based on the analyses I've shown you here today, looks like that's the main form of, and the consortia that are actually doing this are acetate fermenters. Petra Mod is one example of modeling of gas, biogenic gas generation. It allows 3 temperature-controlled calculations for biogenic methane. Gaussian, I believe that the default optimal temperature is too high, but of course, you can change that readily in the program. Constant, yeah, we don't recommend that. And the modified Middelburg approach, you can put in now your initial A value. There's a way of doing that, so you can use the full Middelburg approach for modeling the methane. Middelburg, he showed that TOC from various settings degrades at the same rate with depth, but that initial apparent age really differs, and you need to account for that in your Middelburg equation when you talk about the amount of TOC that's available. One early paper by Pinheiro et al. Erroneously assumed that all TOC is metabolized to form methane and that the apparent initial age, well, they assumed an initial age of 0. Petra Mod has a special option that allows, use of that apparent initial age. Yep. And there are Van Crevelen and carbon to sulfur plots versus depth that can be used to suggest that we're dealing mainly with acetate fermentation in normal marine sediments. Certainly on the order of 20% metabolizable carbon, maybe even less, is available to make methane. The optimal lab temperatures for methanogenesis, they ignore this substrate starvation issue and other factors that that work on these microbes. So these are controversial. The maximum or the actual real best reactivity of lab or in the nature might be as low as 15 degrees. It's probably not 50 degrees C. Acetate, the substrate for these acetate fermenters is rapidly depleted at shallow depth. Depth's actually shallower than most of the methanogens occur. So rate limiting step for methanogenesis is probably the thermal activation of protokerogen to yield acetate. In Biogenics, Chris Clayton uses the kinetics of microbial CO2 as a proxy for generation of acetate, okay? And that's using kinetics from Laurent et al. In 2008. Biogenics basically takes the extent of the reaction and the reaction rate and multiplies them together to get the generated methane, and then adds some additional calculations on diffusion, absorption, and solution within the lithologies that you specify in your model. It's a very nice case study by Hanneke Verveege in 2018 based on a 1D Petra Mod study where they extracted the 1D results and then input those to Biogenics to make their predictions of methanogenic gas. Secondary biogenic gas is a major source of methane. It occurs at low reservoir temperatures, results in pure methane with isotopes sort of in the range of -40 to -55. And there's a nice correlation between the isotope compositions of the CO2 and the methane, and the CO2 is isotopically enriched in carbon-13. Gas hydrate stability zones in permafrost or marine shelf settings depend on temperature, pressure, and salinity, and those are all, I think, pretty well handled by most basin modeling software. So here are some selected references for methanogenesis and hydrates. You can read those at your leisure. Again, I've tried to minimize the number of references here, but this is, I think, a really hot topic right now. So there's some papers in here that really have to be included and looked at in detail. And I think there's a lot of room for improvement here for sure. So here's some more references of the same in the same vein. Okay, let's talk a little bit about something a little more esoteric. Very short discussion of the evidence for biogenic versus abiogenic. There are papers out there that argue for large volumes of abiogenic oil. I think this is, and actually a couple of books by Thomas Gold and others. There's really an overwhelming, I think, evidence that abiogenic gas is, I mean, it's there. We do find abiogenic gas, but volumetrically, it's really insignificant. There's geologic evidence. More than 99% of the reserves that we find of gases and hydrocarbons are in Jurassic and Cretaceous sediments, and the kerogen is abundant and contains microfossils. So this is where the oil is coming from, is these sediments. There's geochemical evidence. We can do oil correlation. We can match the source rock depositional environment with the oil biomarkers and the optical activity in the oil. I haven't talked about that, but optical activity is related to the rotation of plane polarized light, and that's a peculiar characteristic of asymmetric carbon atoms that you find in organic matter that's synthesized by once living organisms. Isotopic evidence, I think, is very strong. Petroleum and kerogen are depleted in carbon-13. Methane is depleted in carbon-13 compared to ethane and propane. That can only occur as a result of a cracking process rather than a polymerization process, as some people would like to see under abiogenic synthesis of gases and oil. Oil source rock correlation, of course, works. And the argument that this is a result of contamination, I think, just simply doesn't make sense. You can correlate, for example, Miocene and Eocene oils in the San Joaquin Basin with their source rocks using isotopes and biomarkers. And it's very clear that the oils and the hydrocarbons are coming from those source rocks. We can do experiments as well. We can generate oil-like products from organic rich source rocks. And we have a biogenic carbon isotope trend for the gases that are made. In other words, the gases are cracked from organic matter, right? And we'd also do kinetics, thermal models based on kinetics and basin history. We know they reliably predict the timing of generation and accumulation, which we can actually validate by looking at real sediments. So just a few very quick slides. You've seen this one before. Microbial gas and thermogenic gases are isotopically quite negative compared to PB. Here's some experiments that were conducted a long time ago by Dave Demaray. I actually was working in the same lab as him at the time he did some of this work. So this is kind of interesting. You can take hexane, hexane gas, and you can crack it at high temperature, and you can generate products. Here's the butane, propane, ethane, methane. And this follows a kinetic or sort of Raleigh distillation type fractionation where the methane is isotopically lighter, more enriched in carbon-12 than the ethane, than the propane, than the butane. That makes sense. When you crack methane from a higher hydrocarbon, which methyl group is going to break off more readily? Is it going to be the C13, which is heavier and harder to break? Or is it going to be the C12 rich methyl group? And fractional conversion would favor then the C12. So the methane gas is isotopically light. However, if you take methane right here and you polymerize that methane, you try to simulate what might occur in the mantle or deep earth and polymerize methane to ethane, propane, butane, you see the opposite isotope effect. In other words, the reactions to make ethane are going to favor an isotopically lighter product, the C12 methane. will react more rapidly to form methane than a C13 and a C12. And you can measure that isotopically. So you see, this is a normal isotope distribution. This is a reversed isotope distribution that you would expect to see in an abiogenic gas. Well, if you look at gases around the world, these are gases from all over the world. All of the gas accumulations, the major gas accumulations, show the normal isotope distribution by carbon number. So these are all thermogenic gases. They're cracked from higher molecular weight organic matter. You can even go to geothermal gases. These are, Yellowstone, the geysers, and they show a normal distribution. So what you have at these thermal, hydrothermal zones is you have circulating groundwaters that are bringing organic matter from the shallow sediments down to depth, cracking it and bringing it up the surface as gases. This is a normal isotope distribution. You do see reversed isotope distributions occasionally. They're very interesting. You can see them in carbonaceous chondrites from outer space, and you can also see them in some gas emanations from Canadian Shield and the Fennoscandian Shield. The isotope distributions look reversed as opposed to normal trend here for these Ontario gases. So no one's arguing that abiogenic gases do not occur. The question is, what's their proportion in terms of the total budget? And it's minuscule. It's certainly a minuscule proportion, at least in the present day, in the geologic past here on Earth. The Earth segregated the hydrocarbons very early in its accretionary history. Here are a couple papers, and actually one book and one paper on abiogenic versus biogenic origin of petroleum. I do want to talk a little bit about mud gas isotope logging. This is a very, I think, very useful technique. It involves taking samples at the wellhead of cuttings and collecting those in an isotube, and then measuring. You can measure on the GC, you can measure the gas composition, but you also measure its isotope composition in the lab. So you get the composition of the total gas and the isotope ratio of the gases, at least the C1, 2, and 3. And so what you commonly see here, this is courtesy of Daniel Dawson and Andrew Murray. These are gases from Australia. You can see here two wells that are drilled not too far apart from each other, and you can see here the trend in the methane isotope value, and the methane, and then the ethane and the propane. And you can see these are actually following trends, so you can actually use the drilling results in one well to predict the drilling results in a well that's not too far away. And this is quite useful actually for a variety of purposes. One of those I'm going to emphasize here would be identifying a seal, an impediment to migration. So here's a wonderful paper by Alain Prinzhofer, and he looked at the log of the ethane to C1 over the carbon isotope value of the ethane, and did some nice calculations here to show that there are very different curves followed by mixing of gases, where you mix a thermogenic gas with a biogenic gas, or diffusion of a biogenic gas through a seal, a competent seal. So here's an example from mud gas isotope logging, a lot of samples with depth from these isotubes. And you see here, you've got a reservoir with isotope composition of the methane around -40. But if you look in the overlying seal and look at those gases, the methane shows a very distinct isotope trend here toward more negative value. Well, what's going to migrate faster through a really a tortuous migration route through a seal, through all these nearly impermeable seal pore spaces? Well, it's going to be the C12 methane as opposed to the C13 methane. So the isotopically light methane migrates faster. And this is a beautiful giveaway here that says, gee, this is a competent seal. It's sealing in certainly much of the methane and the higher hydrocarbons for sure. So here's what those guys look like from this particular well in Africa. That's a diffusion phenomenon that we're looking at right there, as opposed to mixing. So here's another well, again from Dawson and Murray, Andrew Murray, and you can see here we can look at the Prinzhofer plot, and you can see here's the primary biogenic gas. That's shallow. There's the thermal gas, and that thermal gas has a seal above it that you can see in the diffusive fractionation of the methane through that seal. So that's identified an effective seal right there. Okay. Well, we also want to talk a little bit about CO2, and carbon dioxide can be a problem in some parts of the world, like in the Far East. CO2 can represent a major component in produced gases. You want to try to avoid that CO2 if you can. Here are some isotope compositions of different CO2s from out there. You know, marine carbonate, the standard PDB, is around 0. So CO2 from low temperature carbonate metamorphism is going to be around 0. From carriage and maturation, it's going to be negative. Atmospheric CO2, if you're contaminated your sample with atmospheric CO2, it's about -7. There's an equilibrium isotope fractionation between bicarbonate in the water and CO2 in the atmosphere. So you can distinguish these different sources of CO2 in many cases by looking at them. Here's a thermochemical sulfate reduction that produces CO2 that's isotopically negative. And this is a table from John Hunt's book in 1996 that says, gee, we can actually differentiate some of these just by looking at the isotope composition, the carbon isotope composition of the CO2. Diatomic nitrogen, diatomic nitrogen, like in the Rodriguez red beds in the North Sea, you get nitrogen in gases from kind of two origins. Amino groups in organic matter yield ammonia, right? And ammonia from coal and other organic matter can be oxidized to nitrogen on metal oxides, right? So you go from ammonia to N2, diatomic nitrogen. And then there's, of course, the high temperature nitrogen that comes from pyrrolic rings. Here's a pyrrole, and at really high temperature, that nitrogen can break out and form nitrogen. You see some of that in Central Europe. So here's an amino acid. See, the amino group here will break off at very low temperature to form, ammonia, and then eventually, as soon as it hits hits an iron, clays, it'll oxidize to N2. Bacterial sulfate reduction is another one to look at. It's sort of analogous to thermochemical sulfate reduction, but this occurs at low temperatures. Here is the Luan salt in the Gulf of Mexico, and you can see a typical diapir, salt diapir. And these are characterized by limestone and sometimes elemental sulfur within the limestone and the cap, and then anhydrite, and then you have this salt that, of course, lower density, it's moving up through these sediments, and you get oil accumulations and gas accumulations at this excellent seal then between the gypsum or the halite and the carrier sand. Well, there are a lot of reactions that can go on here. This is basically a caprock mineral precipitation is a closed system sulfate reduction based on sulfur isotope data. And the C13 depleted carbonate carbon and low clumped isotope derived carbonate formation temperatures indicate microbial sulfate dependent anaerobic, it's anaerobic oxidation of methane. So here we have basically anhydrite, right? We have sulfate minerals, gypsum, and then we have anhydrite. And anhydrite can break up to form calcium and sulfate. The calcium can combine with any carbonate that happens to be around to make limestone, make calcium carbonate. That accounts for this cap here. And of course, you have microbial methane sulfate reduction. You're reducing you're oxidizing the methane to form carbonate, and that carbonate pulls this reaction to the right, and you're forming hydrogen sulfide, which of course can react, it can be oxidized, and you can end up with elemental sulfur that you see in some of the cap rocks as well. So this is, bacterial sulfate reduction is important in some parts of the world, and the carbonate stable carbon isotope composition is lower than -28, and the carbonate associated sulfate, the sulfur isotope composition, is usually above about +16. So that's a result of anaerobic oxidation of methane. Now there are three types of seals that effectively trap hydrocarbon gases. We talked about permafrost or gas hydrate seals a little bit. That's important, of course, in West Siberia, but also there are evaporites and tight carbonates. Mineralized shales aren't great seals. They're good enough. Arun is gigantic, and Groningen is also a gigantic field. But the real, much better seals are evaporites. So Hugoton, Northfield, and Cutter, that's probably the biggest gas field in the world. They're excellent at trapping gases, and then the factors that limit the commercial dry gas with depth include that excellent seal. So once you get down to very high levels of maturity, you run out of hydrogen. The kerogen or the pyrobitumen yields little methane. Once you get to H2C ratios, about 0.4, or reflectance values over 3%. And diffusion then is going to really affect that methane that you may have generated, and you aren't going to be able to trap it unless you've got an excellent or very good evaporite seal. So that's a great seal. The issue, though, is that evaporite seals are going to contain gypsum or sulfate, and there's sulfate-rich pore waters. So at high temperatures, that methane can react with the pore water sulfate. And that's the analog of bacterial sulfate reduction, except it's inorganic. The calcium sulfate reacts the sulfate reacts with the methane, and to oxidize the methane, it combines with calcium to form calcite, and you form hydrogen sulfide, which of course is highly reactive and doesn't migrate too far. So the effective floor for free methane probably occurs with a rate of diffusion through the seals exceeds that from generation from the source rocks and the pyrobitumen. Certainly that's true in mineralized seals, and but it can go much further in an evaporite seal where you can do this TSR, thermochemical sulfate reduction. Well, that's kind of what happens. It's a two-step reaction. The net reaction, you take the sulfate, you oxidize the organic matter, you reduce the sulfate to H2S, and the organic matter is oxidized to CO2. So you're destroying your accumulation. TSR is nasty business, not only because it destroys the accumulation of oil and gas, but it also produces and can produce huge amounts of H2S, which is an extremely nasty gas to run into when you're drilling a well. TSR and thermal maturity affect the composition a little bit differently. One thing to look at is the isotope composition. They both increase, but here organosulfur is going to increase under TSR, and under maturity, that sulfur tends to break out and escape. So here are some examples from a paper I wrote with Martin Fowler years ago from some of the sour gas pools in the Nisku Formation in Alberta. For the sweet oil pools, you can see, not much going on there in terms of saturates, polars, and aromatics, but you get to the sour gas condensate pools, you're concentrating the aromatics, and the amount of H2S, mole percent H2S, goes up to very high values. Okay, so you're doing this sulfate reduction, and you're forming H2S as a byproduct. And of course, in a carbonate or anhydrate sort of setting, you're not going to have much in the way of clays. Normally, that H2S, if it migrates very far, it's going to run into clays. Metals in the clays, like iron, will precipitate that will result in a reaction with the H2S that forms pyrite, FeS2. But under an anhydrite seal, that H2S can remain intact, and you don't want to run into that when you drill. So here's a little example of the increase in the sulfur isotope. This is relative to the Canyon Diablo troilite standard. And you see the isotope composition with the increasing fraction of H2S, that's increasing TSR, that isotope composition approaches that of the anhydrite seal there in the Brazeau River in Alberta. Here's some examples of some natural gas deposits that are really rich in H2S. These are bad enough, 6, 10%, 15%. But you notice here some of these, South Texas from the Upper Jurassic smack over 98%. Hydrogen sulfide, actually the threshold where people can smell that rotten egg smell is around 0.005 parts per million. So your nose is really sensitive to it until it gets up into the 100 or so ppm concentration. Then you lose your sense of smell, and very soon thereafter you can die. This is pulmonary edema, and really at 800 ppm, that's the 50% LDL, the lethal dose for humans after 5 minutes. So this is really bad because this is not only toxic, but it also eats up normal metals that we use in our drilling equipment. You need special alloys to avoid losing your metals in your wells. So TSR alters the reservoir. High H2S can occur above 80 degrees C, so it's a temperature-driven process. There's some argument about where the optimal temperature is. It's probably on the order of 100 degrees, 120 degrees C. The anhydrate is replaced by calcite. The sulfur isotope of the sulfides and the organosulfur in the oil approach that of seawater sulfate or the anhydrite seal. Sulfur-rich pyrobitumen plugs the reservoirs, and places like Tengiz and Kazakhstan, that's a major issue. Molecular isotope composition of the oils is altered. And so you can look at things like the benzothiophene, the dibenzothiophene ratio that increases with higher maturity. Yeah. There are a number of techniques that you can use to look at solid bitumen that forms as a result of this. TSR, solid bitumen is aromatic and sulfur rich and nitrogen poor. Normal thermal chemical alteration, or TCA, the solid bitumen originates from polars that are rich in sulfur and nitrogen. The aromaticity increases with maturity, but the sulfur and nitrogen remain low. So you can tell the difference between the two of these, right? But certainly with TSR, this can be a real problem. You can overestimate your reserves when it's misidentified as a producible fluid. These solid bitumens on some logs, like the neutron log, actually look like oil, and that was a problem originally in Tengiz. They overestimated the amount of oil that was there because a lot of the pores were plugged by solid bitumen. I'm not going to go into great detail here. There's continuing work on the mechanism of TSR. It looks like it requires these contact ion pairs. Magnesium sulfate appears to be an important component there. Small amounts of labile thermal compounds enhance the rate of TSR. And these labile sulfur compounds seem to be more reactive than inorganic sulfur species. Okay, so there are a number of papers on TSR out there if you're interested in that, if you're working in an area where TSR is a problem. And I leave those for you to look at. Now, this is kind of a summary slide that discusses gas distribution in a deep sedimentary basin. This is the Western Canada Basin from Evans and Stapleton and also Hunt. You can see here we've got low temperature amino nitrogen coming off of proteins, amino acids. We've got some dry gas, which is biogenic methane, isotopically very negative. And with a little bit greater depth, we still generate some methane from amino groups in the organic matter. And we start generating significant amounts of carbon dioxide. This is catagenesis now. We're cracking and making, from carboxyl groups, we're making CO2. And finally, we're making oil. And then when we get to really high maturity, deep in the Western Canada Basin, up against the Rocky Mountain thrust here, we're generating pure gas, methane gas again, in this case isotopically enriched in carbon-13. This is thermogenic gas. And we do have anhydrite, sulfate down there as a seal in some cases, and you can get significant amounts of H2S. So you have these sort of lines that you can follow here that show these types of gases where you can encounter those types of gases along this line. Okay, so reservoir gases, evidence for biogenic origin. We talked about that. There's a lot of it. If you want to go into that in more detail, there are nice papers that describe this. Most exploration geochemists and geologists really don't worry about this anymore. If there were major accumulations of abiogenic gas, they would have been found a long time ago. We've got lots of very deep mines that don't encounter abiogenic gas. And there have been experimental wells even drilled in places like Sweden to try to find abiogenic gas, and there was no abiogenic gas found really. Thermogenic and microbial gases differ in wetness and carbon isotope. Mud gas isotope logging identifies seals that can be used. I didn't talk about, you could use it to predict API gravity and gas-oil ratio and viscosity. Continuous isotope logging can improve interpretations, but there are advantages to both continuous and in discrete sampling here with mud gas isotope logging. Fluid inclusion volatiles. I didn't talk much about those, but they can be used also to identify seal, gas, oil, and oil water contacts. The origin of CO2, look at the isotopes of the carbon. Most nitrogen, diatomic nitrogen, originates as ammonia in shallow sediments from the organic matter, which is oxidized to nitrogen on clays. TSR is a major source of H2S, derived by reduction of sulfate minerals. So here's some papers, some books and papers on reservoir gases that you might want to look at. Well, we've had a long discussion here on gases. There's certainly much more that could be said, but I wanted to limit it to what I thought were the significant factors to talk about. So in review, we've had 6 lectures now. All of these have focused on really the importance of geochemistry as both input and as a calibrant in basin models. And you see this figure that we had in our very first lecture. Geochemistry is really important in the input here, the kinetics, the organic richness, the kerogen type, and then we use the geochemistry here to calibrate the models. We can use vitronite reflectants or other calibrants to calibrate that model and iterate the results here. So we have a model that is calibrated and is useful for our predictions. Of course, as we come back to that classic quote from the statistician George Box, all models are wrong, but some are useful, and that's really what we're after. We're after useful models here. So the details of the model may not be exactly correct, but hopefully we have a model that can be used for prediction. Again, here's a review of what we talked about. This is available now to our students and to the faculty in BPSM and also our affiliates. Origin and preservation of organic matter, vitronite reflectants, not as straightforward as a lot of people think. Same with Rocky Val, pyrolysis and TOC, kinetics, geochemical correlation, and gas geochemistry. Again, I touch on these and other topics in much more detail in a much longer course. These 6 lectures are certainly less than a full day of time that anyone could devote to them. I hope that these lectures have been useful to you. I am certainly available. If you want to send me an email, get in contact with me or any other of our co-principals to talk about details that we mentioned in the course, and we're here and available for consultation. Thanks very much for your attention.